Hello everyone, it's July the 5th. I think I got this log wrong. Yeah, I missed one. Yeah, guys, that's fine. Alright, let's do this. We have an easy question, which means we have to dig into binary lifting today for sure. I've done this before. N people standing a line labeled 1 to n. The first person in the line is holding a pillow. Every second, the person holding the pillow passes it to the next person standing in the line. Once the pillow reaches the end of the line, the direction changes, and the people continue passing the pillow in the opposite direction. For example, once the pillow reaches the nth person, they pass it to n-1. Given two positive integer n and time, return the index of the person holding the pillow after time seconds. So every second passing to the next one. So n is supposed to have 4 people 5 times. So we go 1, 2, 3, 4, 5. The answer is 2. Alright, we just need to figure out how the modulo works, right? So we have 1, 2, 3, 4. 4 people. And we'll go 5 times. So can we say, 5 mod 4, that would be 1, right? So the 1, 2, 3, but each second is, so it's actually not, it's going to be 3. That's right, modding could be 2. But 2 is going this direction. Yeah, it depends on which direction you're going. So we need to do div mod. Right, so 5 divided by 4 is 1, so we know we'll go odd number, right? We'll go odd, and then we do 2, so from the end, so 4 minus 2 will equal to 2. So in this case, n equal to 3, time is 2, so we do 3 divided by 2 equal to 1, which is odd, so we go in this direction, and 3 mod 2 is equal to 1. So it'll be 3 minus 1, because I go back, so equal to 2. That is not right. Oh, because 3, it's actually 1. No, my bad. No, that's it. It's time. It's time divided by n minus 1. Alright, time divided by n minus 1. This will tell you either odd or even. And then we'll do is n either 1 plus t mod n minus 1 or n minus t mod n minus 1. So in this case, t divided by 2 is 1, so I know it's odd. And if it's odd, we go here. This is odd, this is even. So it will be 3 minus t, so it'll be 0. Yep, so that is the solution. Alright, so what we're gonna say is if time divided by n minus 1 mod 2 is equal to 0, even, we'll return 1 plus time mod n minus 1. Otherwise, return n minus time mod n minus 1. Yeah, I think I can write that here as well. 2552. There's nothing I need to write. Let's just test this. I can throw a few. N is 1000, time is 1000, n is this, time is this. Looks to be solid. I'm going to submit it. And it will pass. All right, that was good. Okay, so that's that. All right, I want to back to the binary lifting. You just have to. There's no avoiding it. There's no avoiding it. You have to go binary lifting. All right. Binary lifting. Q queries from KV. We want to find the kth ancestor of V in the tree. One simple yet quite inefficient way of solving this problem is to build for every node an edge towards its direct ancestor. Then, in order to solve a query, simply have traverse k edges. And this approach has a complexity of O and Q. We can try improving by adding some jump edges. Jump edges. A jump edge is simply an edge that starts from the node and is not directed towards its parent, but towards an arbitrary ancestor. These jump edges will allow us to traverse large regions of edges in a single operation. Let's start by building jump edges from each node towards its second ancestor, fourth ancestor, eighth ancestor, and so on. Note that in the above figure, only a subset of these jump edges is visible, since otherwise it will clutter the image too much. So I think the black is 1 parent, the red is 2, and the blue is 4, and the green is 8. Let's define the length of jump edge as the number of normal edges that are skipped by traversing this jump edge. For example, all the blue edges have length 4. Yeah, because I skipped 1, 2, 3, 4. Skipped 4 edges. We can compute the destination of these jump edges in a recursive manner by using already computed short. That's very important. Compute the new jump edges by recursively using the already computed short edges. So what this means is if I want to compute from 9 to do 4 jump edges, right? I don't have to go there one by one. Instead, I can do 9. I can go to 7, a 2 jump, right? I do 2 jump, and then I find from 7 as a 2 jump. So that is one very important part of binary lifting, which is if I want to compute, let's say ancestor, right? If I want to compute ancestor 9, and here, usually it's index. That's like if we say this is j, right? So it's like 2 to the jth ancestor. Okay, so if I want to compute ancestor 9, 2, right? So this will equal to ancestor 9, 1, and then 1. So we say more generally ancestor v going j shall equal to ancestor v going j minus 1 and then j minus 1, which means if you compute the smaller ones first, then you will be able to compute the big ones. I think that's exactly the recursive relationship that I just showed, right? So this is the node to the ith, so equal to actually I think it's the ith node, the ancestor of I, right? Ith node with the 2 to the h, right? So it will be I, which is my v, j minus 1 is h minus 1 to h1. Yeah, that's exactly what we're talking about. So by doing this, we just making bigger jumps, right? We make a bigger jump so we can improve. Okay, now can we do better? In this particular case, we can exploit the fact that the queries are given in an offline manner. We can read all queries at the beginning and solve them together. We will explore the tree using a DFS, and we'll maintain in an array all of the ancestors of the current node, including itself. To maintain this array of ancestors, we can simply do the following. When going from a node to its son, we push the son to the end of this ancestor array, and when returning from a node to its father, we remove it from the end of the ancestor array. As such, when we reach a node, we can easily answer the queries related to it by accessing the array of ancestors. However, what could we do if we first had to answer a query before getting the next one? We are not able to improve the complexity better than this. However, we can reduce the required memory. One way to reduce memory without sacrificing execution time. Actually, I need to read this one more time. We can read all the queries at the beginning and then solve them together. We'll explore the tree using DFS, and we will maintain in an array all of the ancestors of the current node. To maintain this array of ancestors, we can simply do the following. When going from a node to its son, we'll push the son to the end of this ancestor array. And when returning from a node to its father, we remove it from the end of the ancestor array. As such, when we reach a node, we can easily answer the queries related to it by accessing the array of ancestors. So this is as we go through, we will just keep pushing the ancestors. One way of reducing required memory is to sacrifice time efficiency and change the base of the length of the jumps. The powers of another integer using the method we have complexity. We can reduce the memory to OM without massively impacting the execution time. We can compute for each node its direct ancestor and a single jump edge toward an arbitrary ancestor. When searching for the kth ancestor, we'll try to traverse the jump edge if it does not pass over the kth ancestor just like before. One way to choose the destination of these jump edges can be observed in the following picture. Let's denote the direct ancestor of x as parent x. We'll add jump edge x to y only if the jump edges from parent x to z and the z to y exist and have the same length of an arbitrary z. It is easy to see that we can compute all such jump edges when we're processing the tree from top to bottom. I don't understand this one. So basically what this says is we just jump. You do a binary lifting. So if you're giving me a number, right? And then I just pick the jump, we pick the large jump closest, but not exceeding closest to it. And from there, I'll walk. Not walk, and from there, I'll do another one. I'll do another one. Basically, basically just breaking down. Like, if I want to do a jump of, let's say, 7, right? And 7 can be broken down to 1, 1, 1, right? So what I can do is from whatever node, I'll do a 0, 1, 2, right? I'll do an ancestor, let's say source a 3, no, a 2, because that's 0, 1, 2, right? I'll do a source 2. And then after that, we'll do this, will be ancestor this, will be source 1. And then we'll do an ancestor of this, right, with source 0. So that will be giving you 7. So basically, from the source, we'll jump 1, 2, 3, 4, right? 1, 2, 3, 4. We get to another source, S prime. And from S prime, we'll jump 2 to S double prime. And this would jump to the destination. And altogether, 1, 2, 3, 4, 5, 6, 7. Ah, that makes more sense. That makes more sense. So each one will be n plus q. Yeah, n plus q is we have to traverse. Wait, hold on. Why n plus n log n plus q log n? Okay, n log n. N log n is the construction. All right, n log n is the construction of the binary lifting, and q log n is the time complexity of going through the queue, right? Going through queue queries. And you say we can do better by changing the base. Oh. Yeah, so this basically says, if we have all Q queries at the start, you look amazing. If we have all Q queries at the start, then we can very simply, because I know which one will be asked, right? Then as I DFS the tree, I will keep an array of ancestors, right? I'll keep an array of ancestors. And then if I keep an array of ancestors for each node that I encountered so far, and then if that node need to be queried, so I can look into that array and very quickly to get its kth ancestor. So that is if I know the queries. So we can make it fast, like O(n plus q. That would be sufficient. However, if we do not know the query beforehand, we have to answer them one by one, then it cannot be better than O plus q log n. Well, of course, instead of doing length of 2, yeah, we can tweak this, right? Instead of power of 2, we can do power of 3, power of whatever you want. And that can make it faster because it will be d log. It might be, actually. It might be faster. And then they say we can do O(n). Oh, I think it's reduced memory to O(n) instead of O(n log n). But I think the time complexity cannot be better than that. Okay, so anyway, but this is what I really want to read again, which is binary lifting to find the lowest common ancestor. So now we have this binary lifting set up for each one, so I know its ancestors. So to find its lowest ancestor, so I have 2 nodes, right? Basically, we have this ancestor array, right? We have this ancestor array, which have a vj, which will calculate the 2 to the jth ancestor of node v. Then if I give you, so given, now I say given u and v, find their lowest common ancestor, right? Using the binary lifting matrix, we call it matrix, binary matrix A and C. Okay, so what I think, from what I understand from the other day, is we'll just do we'll set a ancestor, I call it A, equal to ancestor U, and we do a K, right? K is, so 2 to the K. 2 to the K is smaller or equal to the largest. I think it's equal to floor, right? Floor log 2n. Now K is, my bad, K is this. So K shall be the largest. K is the largest integer such that 2 to the K exists for this ancestor. But how do we know that? Well, we can just compute, right? So A is that. And then what we need to do is just see, because A is the ancestor of U, we need to see if A is ancestor of V, right? And if A is ancestor of V, then we can reduce. So we compute, so it's A0, right? We'll say A1 is ancestor U K minus 1, right? And then until we do an A, we say AP is ancestor U K minus P, and it's not an ancestor of V. So it's too much. And then we will say U will equal to AP, right? Because we have something that's not the ancestor of V. So we put AP back to U position, and then we'll find ancestor U again, K minus P minus 1. I think that's the algorithm. So because AP is from U, we do K minus P steps up, right? And they say this is too much. So we say that from that position, because if I do K minus P again, right, from this position I do K minus P again, then let me think. Because the previous one is K minus it's something, right? And that didn't work. So I divide it by half, right? Divided by half. So yeah, if you divide it by half, that means if you go K minus P again, that will be the same position as what we had encountered before, right? We had encountered before. So in minus 1, we get it lower. So you just keep doing this until you hit this equal to 0. Because when you hit equal to 0, there's no more place for you to go. Okay. Another common, let's just read this one. Another common application is computing the lowest common ancestor, LCA of 2 nodes. In addition to pre-computing our jumps edges, we should also compute for each node its depth. Yes, because you need to know whether a node is the parent, is the ancestor of the other. So to do that, when you hit a node, you will compute its depth. Yeah, your depth has to be smaller than the other one in order to be its ancestor. We're using the original method to create jump edges. Let's assume the depth y is smaller than x. Otherwise, we can just swap them. Okay. Let k equals the difference in depth and z be the kth ancestor of x. The LCA of x and y is the same as the LCA of y and z. Since the depth of the LCA is at most the depth of y that is equal to the depth of z, we can substitute x, y, z, and from now on assume that depth x and depth y is the same. Okay, so they use this little trick to say we'll have the same depth. If x equal to y, then we can stop since the LCA is clearly x. If the direct ancestor of x is equal to the direct ancestor of y, we can also stop since that direct ancestor is LCA. Otherwise, let k be the highest power, that's the one, let k be the highest power of 2, lower than or equal to the depth x. If the kth ancestor of x and the k ancestor of y differ, then we can reduce the problem of finding the LCA of, so the kth ancestor is different than the kth ancestor of x. Otherwise, if the k ancestor are the same, from now on we should only consider smaller jumps. Yeah, kth ancestor is the same, so we reduce and then we jump again, and we reduce, we jump again. So this is slightly different from how this one explains, right? This is slightly different from how this one. Well, let's see which one I like better. So basically it says if the two have different depths, right? And if one, yeah, if they have different depths, then I'll make them the same depth, right? I'll make them the same depth, okay? And then we'll find the top. If they share, then we will minus 1. Share until they don't share, then we'll move up and then we'll find again. Okay, that's this. This one's slightly different. Okay, this one's slightly different. This one says we'll remember the time of the first visit of this node, which essentially is depth, right? And the time when we left it. In constant time, for a node is an ancestor of another node. So when we enter or when we left. So they use that, right? So its ancestor is if the time in is smaller than the time in of the other, and the time out is larger than the time out, so that is an ancestor. Okay, so the LCA is we'll see if they're the ancestor already. If they are, then it's we're good. If they're not, then what the hell is L? I forgot. L is the largest ceiling, right? L is the largest ceiling. So yeah, we do the largest ceiling, right? As ancestor, we do the largest ceiling. And if it's not ancestor, I move it up, right? And I will always minus minus. And if it is, I also move up until I become 0, then we'll return this. Yeah. So in the other solution, we have 2 nodes and we'll record the depth. Okay. So the difference in the depth is the kth ancestor, right? So we basically do a kth ancestor, and then we'll find a kth ancestor, and if this kth ancestor is the same, right, then that is the common ancestor. If kth ancestor is not the same, then we have the two on the same depth, right? They're on the same depth, and we go from the top. Yeah, again, from their position, we go from the top. Now, how do we go from the top from any position? Right? We need to know at this position what is the largest drop it has. Well, do we know the largest drop? Well, we have the depth, so we do know. So we find that the kth, right? If the same, we find -1. If it's to this, and then we'll move both up. I don't know, which one do you like better? I actually want to implement this one, because this one requires the kth ancestor, and I want to implement kth ancestor. So we'll do, right, we'll traverse everything. And how do we compute this ancestor matrix? Well, we compute the ancestor matrix by, well, we're DFS, right? So we are the current node. So I can set 0 because I know its parent. So DFS, I'll pass the parent. I have the current node. Okay. And then I say the current node ancestor 0 is equal to parent. And then we need to go through the whole thing until the depth is, yeah, because what I want to do is like 2 to the power is smaller than its depth, and I can, you know, handle all that, which I think is almost the same as this one, how we do it. But this will go all the way to L, which I don't think is necessary. Yeah, I don't think it's necessary. Do we have a problem, say, kth ancestor? I think I want to try kth ancestor first before I solve this one. It'll be more fun. Surely it will be more fun. There we go. Yeah, let's try this one first. Have I done this? I've never done this before. Kth ancestor of a tree node. Yep, let's do that. All right, let's do that. Yeah, this is one of those. If you don't know, binary lifting, I think will be. Actually, no. There are ways to do this. Right? There are ways to do it. Oh, this is a different setup. Okay, this is a different setup. You get it every single time. Yeah, this has to be binary lifting. Okay, that's all right. All right. We've gone through binary lifting again. I think I have a much better understanding of it, and we're gonna tackle it some other day. All right, I'll see you guys.